In this final video about integration, I'm going to explain how to use our ideas about how to integrate functions to come up with a very general, very easy formula for how to integrate curves in submanifolds of Rn. So just in general manifolds. So how to integrate differential forms over parameterized manifolds in general in Rn. So let's say parameterized, to be specific, parameterized K-manifolds, and we're going to be talking about differential K-forms. So I'll sort of move everything. Okay, so when we were talking about integrating functions, we were actually, I said we were integrating a function, but secretly we're really integrating the volume form, which is an n form over a region in Rn. And we have our change of coordinates formula. So it's basically saying if I have some map phi from Rn to Rn, then the integral over a region of f dx1 through dxn is just equal to the integral over phi of the region, and then phi inverse pullback of f dx1 through dxn wedge. So why not? Why do I have to be pulling back the why do I have to be pulling back the volume form? I could be pulling back whatever, the heck form I want, right? So in general, a K form eats K vectors. And if I want to integrate over a K manifold, I just pull that form back under some parameterization. So let's assume I have some map. So I have some map. So now let's generalize to the case where phi inverse, this is a little bit tricky, but phi inverse is a subset of RK. And sorry, phi inverse is a map from a subset of RK, U, to Rn, where U is a subset of RK, and phi inverse is a parameterization of sigma sub k, which is some just the image of U under phi inverse. So what I mean is that I want phi inverse to be injective and also differentiable. And so, okay, so phi inverse is a little bit confusing. So why am I calling this phi inverse? Well, secretly, phi inverse is the inverse of a coordinate chart. So if I have my manifold sigma k is some smooth, so how does this work? It's a smooth K manifold in Rn. So I know I usually switch the n and the k, but just bear with me, please. So again, let's just use our favorite friend, S2 in R3. And then I have some coordinate chart, which takes some blob, right, and takes it to just another blob in R3. And because it's a coordinate chart, it takes its intersection with the manifold sigma k to the xy plane in R3. So here I'll draw this back again on top, so you can see everything. So it's taking the intersection with sigma k to R3. So phi inverse is the inverse. So what I think of this is phi inverse being the inverse to some function phi, which goes from Rn to Rn, but it's sort of it's the coordinate chart, and phi inverse is really sort of the literal phi inverse restricted to the xy plane in this case, or more generally the set where the last n minus k coordinates, that looks like an h, are 0. So phi inverse is really the inverse of something, but I can also just think of it as the parameterization of my manifold by something. And in this setting, I can just rewrite my old pullback formula, but now instead of inputting, function times the volume form, I can input any k form I want, because now U is a subset of RK. So that k really looks like an n, so I better change it. U is a subset of RK, so now I can integrate the inverse pullback of my k form, and it will be some function times the volume form. So if alpha is a k form on Rn, then the integral over sigma k, some k submanifold of alpha, is defined to be the integral over phi of sigma k intersect sort of the last n minus k coordinates equals 0, which I can also just write this as u, right? This is the domain of phi inverse of phi inverse pullback of alpha. So this is my definition of how to integrate a k form over a k-dimensional manifold in Rn. Okay, so let's do the simplest examples of line integrals and surface integrals. And on your homework, you're going to explore how the surface integrals are related to the surface integrals you were doing in multivariable calculus. So we'll do the example, line integrals. So let's so there's an example in your book, so we'll do the first part of it, but we won't do the second part. Okay, so I want to discuss, well, actually, let's do the second part. It's maybe more fun. So we're going to have my curve, my sigma 1 is going to be the arc of the parabola, x equals 4 minus y squared, from -5, 3, -3 to 0, 2. So this is in R2. Okay, and I could do this in R3 as well. There's an example in your book, actually, in the line integral section, where there's an example in R3. But let's just do it in R2. So what is this? This is, I want to take the xy coordinate plane, and let's actually put a grid on this, because this is not, these aren't maybe the most obvious points to draw. So -5, 3. I better have enough space to do this. -5, -3. So -5, 1, x, y, 1, 2, 3, 4, 5, 1, 2, 3, to 0, 2, which is right here. And I want the arc of the parabola 4 minus y squared. 4 minus y squared is going to go through the point 4. And then it will also go through, let's see, it'll also go through the point when y is equal to 1, it'll go through the point 3. So it'll go through here and there, and then also here. So I can just draw this. And when I discuss a curve and I say it's from something to something, what I mean is what this means is I want to parameterize the curve so that the positive x direction, like the positive r direction, goes points in that direction. So I should parameterize it in that way. So what I want is phi inverse to go from some subset of R to R2, and I want it to take the point, T to the point 4 minus T squared for X, and T for Y. And that's just generally how I can parameterize any sort of graph in, this is a graph of X in terms of Y, but it doesn't matter. Any graph in R2. And this is good because when I plug in t equals, let's see, if I plug in just like t equals 0, and then increase t, like the smaller value, sorry, when I plug in t equals -2, I'm here, and when I plug in t equals +2, I'm here. So I am going sort of in the right direction. So let's get rid of those. Okay, so this takes you from -3 to 0, 2. And then I want to integrate the one form alpha equals y squared dx plus x dy along this curve. So my formula tells me to integrate from, okay, so this should be, if I want to parameterize sigma 1, u is going to be the set that goes from -3 to 2. So then what I should be doing is the integral over sigma 1 of alpha is equal to the integral from -3 to 2. That's equal to phi inverse of sigma 1. And, or sorry, phi inverse phi of sigma 1. So the inverse of phi. And I should be pulling back using phi inverse alpha. So I need to okay, so now I need to compute this. So remember, phi inverse pullback is just the transpose. So I need to first compute the d of phi inverse. So d of phi inverse is, so it's going to take, it's going to be a column vector because it's going to take one number and turn it into 2. So this will be -2t, 1. And then, so then phi inverse transpose applied to dx is going to equal -2t, 1, 0, which is going to be just the number -2t times dt. I mean, so, right, so this should be giving me a one form on R, so everything is just going to be times dt. And phi inverse pullback dy is equal to -2t, 1, 0, 1, which is just going to be dt. And then I also need to multiply by y squared and x. So y squared is equal to t squared, and x is equal to 4 minus t squared. So what I end up getting as phi inverse pullback y squared dx plus x dy is equal to t to the 4th times -2t dt plus 4 minus t squared dt, which is all together -2t to the 5th minus t squared plus 4 dt. Okay, so then what I need to do is now put this all together. So I need to compute this by plugging in phi inverse pullback. So plug this in exactly here and integrate that. So this is something I can now integrate, and it's not so hard. It's going to be some number, which I'll leave that to you. Your book will help you calculate it. It's on page 247 if you want to check. Okay, so that's that. So now let's do the second example. So let's do a surface integral.